Human strength is influenced by a number of biomechanical factors that together determine how much force a person can produce. These factors include neural control, muscle cross-sectional area, muscle fiber arrangement, muscle length, joint angle, muscle contraction velocity, joint angular velocity, and body size. Let's break down each of these factors and their contribution to strength with specific examples to provide a deeper insight into the mechanisms involved. So, neural control plays a critical role in determining the amount of force that can be generated during a muscle contraction. Specifically, it determines which motor units are recruited, muscle fibers innervated by a single motor neuron, and the rate at which they fire. The more motor units that are recruited and the larger the motor units, the greater the muscle force that can be generated. A common example of this neural factor at work is seen in the early stages of resistance training. Novices experience rapid strength gains not because of increased muscle size, but because their brain is learning to more efficiently recruit motor units. This phenomenon is called neural adaptation. For example, during the first few weeks of performing a squat, trainees will notice they can lift more weight due to better motor unit recruitment and firing rates, not due to changes in muscle size. Over time, this early phase of neural gains gives way to slower hypertrophic growth as muscle fibers adapt to training. The force a muscle can exert is directly proportional to its cross-sectional area, CSA. This means that larger muscles with a greater cross-sectional area can produce more force. However, volume does not necessarily equate to strength. For example, two athletes may have the same muscle cross-sectional area in their biceps, but if one is taller, their longer muscle fibers may result in a greater volume of muscle without an increase in force production. A practical example of the importance of muscle cross-sectional area can be seen in elite gymnasts who typically have smaller frames but extremely well-developed muscles relative to their body size. Their muscles are highly efficient at producing force, which allows them to perform bodyweight movements such as pull-ups or planches with ease. So despite not being bulky, these athletes have a high muscle-to-weight ratio, optimized for lifting and controlling their body. The arrangement of muscle fibers is another factor that impacts strength. Muscles can have different fiber orientations, which affect both the amount of force they can produce and their shortening velocity. Pennate muscles, for example, have fibers arranged at an angle to the direction of pull, which allows for a greater number of muscle fibers to be packed into a given area. This arrangement increases force production at the expense of speed. An example of a pennate muscle is the rectus femoris in the quadriceps, which is optimized for producing large amounts of force during movements like squatting. In contrast, muscles with a parallel fiber arrangement, such as the biceps brachii, produce less force but can contract more quickly. This allows for faster movements, like in a bicep curl, where speed is a factor in performance. Muscle length plays an important role in determining the force a muscle can produce. At its resting length, a muscle can generate maximal force because the actin and myosin filaments are optimally aligned to form the greatest number of cross bridges. However, if the muscle is stretched too far or contracts too much, the overlap between these filaments decreases, reducing the number of cross bridges and consequently the force the muscle can generate. A simple example of this can be observed in deadlifts or squats when the muscles of the lower body, such as the hamstrings and quadriceps, are at their optimal resting length. They can produce the greatest amount of force. As the lifter stands up from the bottom of the squat, the muscles stretch and then contract, with peak force being generated when the muscles are closest to their resting length. The angle of a joint also influences the amount of force a muscle can generate. Force is transmitted across a joint as torque, and the torque a muscle can produce varies depending on the joint angle. This is because of the changing moment arms, which represent the distance between the muscle's line of action and the center of the joint. For instance, in a bicep curl, the joint angle that allows for the most torque occurs when the forearm is horizontal to the ground. At this angle, the moment arm is at its longest, requiring the most force from the biceps to complete the curl. As the elbow flexes and the forearm moves away from this position, the moment arm shortens, making the lift easier. As the speed of a muscle contraction increases, the force the muscle can produce decreases. This relationship is known as the force-velocity curve. At slower contraction speeds, muscles can generate more force. This is why heavy, slow lifts like powerlifting movements, deadlifts, squats, allow athletes to lift maximal weights. On the other hand, high velocity movements like sprinting or jumping require muscles to contract quickly, which reduces the total force they can produce. The balance between force and velocity is an important consideration in sports performance. For example, Olympic weightlifters who perform explosive movements like the clean and jerk rely on a combination of both force and velocity to lift the bar as quickly as possible while maintaining high force output. Joint angular velocity refers to the speed at which a joint moves through its range of motion. This concept is tied to the type of muscle contraction taking place: concentric, eccentric, or isometric. During concentric actions, when a muscle shortens as it contracts, force production decreases as the speed of contraction increases. Conversely, eccentric muscle actions, where the muscle lengthens under tension, can produce greater force even as speed increases. An example of this principle is seen in eccentric training, where an individual focuses on the lowering phase of a movement, such as the descent during a bicep curl. Because the muscle is stronger eccentrically, this part of the movement allows for greater force production, often leading to greater muscle hypertrophy and strength over time. The strength to mass ratio is a crucial factor in activities that involve moving the body through space, such as sprinting or gymnastics. Athletes with a higher strength to mass ratio can accelerate their body more effectively. For instance, if an athlete increases their body mass by 15% but only increases their strength by 10%, their ability to accelerate will be compromised. This is why gymnasts and the sprinters often focus on maximizing strength while maintaining a relatively low body weight. In weight class sports, such as powerlifting, maintaining an optimal strength to mass ratio is essential. Larger athletes tend to have a lower strength to mass ratio due to the fact that muscle volume, which increases with the cube of body size, grows faster than muscle cross-sectional area, which increases with the square of body size. This is why smaller athletes often excel at relative strength feats, such as pull-ups or bodyweight squats. Body size impacts strength due to the relationship between muscle cross-sectional area and muscle volume. Smaller athletes generally have a higher strength to mass ratio because their muscle cross-sectional area increases at a slower rate than their muscle volume. This means that pound for pound, smaller athletes tend to be stronger than their larger counterparts. For example, a lighter Olympic weightlifter may lift close to the same amount of weight as a much larger competitor, even though the larger athlete has more muscle mass. This is due to the smaller athlete's greater relative strength, meaning they can lift more weight relative to their body weight.